Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Usually when you look at a photograph, there is an inherent trust in what you are seeing.
Right, you take it at face value.
Exactly. You look at a picture of a vast sweeping landscape, and you might notice a tiny, indistinct red dot in the background.
Yeah.
And your brain immediately categorizes it. You think, okay, that is just a pebble, or maybe that's a distant leaf. You trust that the simplest explanation is the right one.
Because the universe is supposed to make a certain kind of intuitive sense.
Right. But imagine you take that exact same photograph and you hand it over to the greatest digital enhancement team on the planet.
Okay, I'm tracking.
They zoom in on that tiny, seemingly insignificant red dot. They clean up the image, and suddenly you realize it is not a pebble at all.
It's something else entirely.
It is a massive, towering mountain, and the entire thing is violently on fire.
Wow.
Suddenly, your entire understanding of that landscape, like what belongs there, how it's formed, what the rules of that world actually are, it is completely shattered.
I see where you were going with that, but the mountain analogy almost understates the problem.
Wait, really? Understates it?
Yeah, I mean, finding a mountain where a pebble should be is surprising, sure. But what we are dealing with right now in the astrophysics community is far weirder.
Weirder how?
It is more like zooming in on that red pebble and realizing it's a functioning nuclear reactor.
Oh, wow.
It is not just a matter of scale. It is a matter of something existing in a time and place where the fundamental laws of the environment shouldn't allow it to exist at all.
Right, because the landscape we were talking about isn't a forest. It is the dawn of the cosmos itself.
Exactly. And those tiny red pebbles have turned into one of the most baffling mysteries modern science has ever encountered.
We're talking about something that is fundamentally breaking the rules, and it all revolves around the James Webb Space Telescope.
The pinnacle of our observational technology.
Yeah, I mean, for a long time, humanity has been pointing telescopes at the night sky, hoping to see further and further back into our history. And the James Webb Telescope is not just looking at stars.
No, it is looking at the very beginning of time.
Right. It is effectively peering into the universe when it was an absolute infant, like less than 1 billion years old.
Barely out of the cosmic cradle.
And what it is finding out there, in the deepest, darkest, oldest reaches of space, are these mysterious objects that astronomers are simply calling little red dots, or LRDs.
Catchy name, right? Very literal.
They usually are. So today, our mission for you is to unpack exactly what these mysterious dots are. We need to figure out why they have caused such a massive headache for the physics community.
It is a huge headache.
And we're going to explore how a brand new, totally groundbreaking astronomical model might finally be the key to explaining them.
To really grasp the magnitude of this mystery, you first have to understand the rigid expectations we had going in.
Right, we had a rule book.
Exactly. When you look at the universe at that incredibly young age, you have a very specific set of expectations based on decades of cosmological modeling.
So what did we expect to see?
You expect to see the raw building blocks of things, young, chaotic, unstructured galaxies just starting to pull themselves together out of primordial hydrogen and helium.
Just a messy soup of gas.
Yeah, just the earliest, somewhat modest stars coalescing. There is a whole established timeline of how the universe grew up, how matter clumped together, and how long it takes for complex structures to form.
And these little red dots completely bypass that timeline.
Profoundly. Finding them in that specific era is jarring.
I was thinking about how to explain this feeling of finding something so out of time. Yeah. Imagine we finally invent a working time machine.
Okay, I love a time machine analogy.
We send a team of scientists all the way back to the Jurassic period. Their mission is to take photographs of the dinosaurs and bring them back to the present day.
So we can finally see the real Jurassic world.
Right. So they come back, they develop the photos, and everyone is gathered around to look. Sure enough, there is a magnificent T-Rex in the center of the frame.
Perfect. Mission accomplished.
But then you look a little closer at the T-Rex's tiny little hand, and it is holding a modern smartphone, completely powered on, screen glowing.
The anachronism part of that works beautifully. But let me push back on the smartphone idea just a little bit.
Why?
Well, a smartphone implies a highly advanced, organized civilization operating in the background, you know.
Right, someone had to build the factories, write the software.
Exactly. But what we are seeing in the early universe isn't a complex, organized structure like a phone.
So what is it like?
It's more like finding a perfectly refined, unimaginably powerful jet engine just sitting in the middle of the Jurassic jungle.
Oh, wow.
Yeah, just running at maximum thrust with no factory anywhere in sight to have built it. It's raw, terrifying power that hasn't had the necessary time to be constructed by the normal processes of cosmic evolution.
Okay, that makes total sense. It's the raw power and the complete lack of a factory that makes it so weird.
Precisely.
You would look at that photo and say, wait a minute, this is impossible. The conditions to forge that kind of engine shouldn't exist for billions of years.
And that is exactly the feeling rippling through the astronomical community right now.
They are looking at the oldest images of the universe, expecting to see the primordial soup, and instead they find something that defies all our current rule books. Okay, let's unpack this.
Let's do it.
How can something so small, literally just a dot in a telescope image, cause such an absolute fundamental headache for physicists?
Well, to understand the solution, you first have to understand the sheer weirdness of the clues at the scene of the crime.
Scene of the cosmic crime.
Right. We have to look at the specific physical properties of these little red dots because it isn't just one weird thing about them.
It's a combination of things.
It is a highly specific combination of clues that, under every single established astrophysical model we currently rely on, absolutely do not belong together.
Let's lay out the evidence then. We are the detectives arriving at the scene. What exactly are we looking at? I assume they aren't just calling them little red dots for fun.
No, astronomers are very literal with their naming conventions.
Right, like the very large telescope.
Exactly. So the first clue is the little part. They are incredibly compact.
How compact are we talking?
Well, when you look at a typical galaxy from the early universe through the James Webb Telescope, it usually looks like a smudge.
A smudge.
Yeah, it's a sprawling, messy cloud of stellar formation. It has a physical extent that we can actually measure in pixels.
Okay, so it has shape.
Right. But these LRDs, they don't look like sprawling galaxies. They are what we call unresolved.
Unresolved, meaning what exactly?
Meaning they are tight, distinct, concentrated points of light. They are so small that even our most powerful telescope cannot see their edges or any internal structure.
They just look like single piercing pinpricks. But wait, are we sure the telescope isn't just malfunctioning? Or maybe it's just a smudge on the lens or some dust in our own solar system getting in the way?
It's a totally fair question, and honestly, it's the first thing astronomers check when they see anomalies.
Right, rule out user error first.
But these aren't artifacts. We know they are real and incredibly distant because of the second clue, their color.
The red part of little red dots.
Yes. They are distinctively, intensely red. Now, in astronomy, red is a very loaded term. We have to explain what redshift is to really get why this matters.
Right, because things in space aren't just red because they are painted red. It has to do with how light travels over vast distances.
Precisely. The universe is expanding, right? And it has been expanding since the Big Bang.
Okay.
Because space itself is stretching out, any light traveling through that space also gets stretched out.
Like drawing a squiggly line on a rubber band and then pulling it.
That's a perfect way to visualize it. So if a star emits visible blue or ultraviolet light in the early universe, that light has to travel for over 12 billion years to reach our telescope.
And during that 12 billion year journey,
the space the light is moving through expands, and the light waves get physically stretched.
So the wave gets longer.
Yes. And the longer a light wave is, the further down the electromagnetic spectrum it moves, shifting toward the red and infrared end of the spectrum.
This is cosmological redshift.
Exactly.
So James Webb is actually an infrared telescope specifically designed to see this stretched out light.
It was built for exactly this purpose.
The fact that these dots are red tells us they are unbelievably old and unbelievably far away.
That is half of it. The redshift tells us they are from the first billion years of the universe.
What's the other half?
Dust.
Dust. Just normal space dust.
Yeah. If you have a very bright object, but it is surrounded by a thick, dense cloud of cosmic dust, that dust will scatter the shorter blue wavelengths of light.
Oh, like a filter.
Right. It only lets the longer red wavelengths pass through. Think about a sunset on Earth.
Okay.
The sun looks red at the horizon because the light has to pass through more of the Earth's dusty atmosphere, which scatters all the blue light away.
Okay, so we have a tiny, tight little point of light. It is very far away, and it might be surrounded by dust, making it look even redder.
Yes.
That still doesn't sound too crazy yet. I feel like we have compact, dusty things in space all the time.
We do. But here is the third clue, and this is where the physical contradiction really begins. They are extremely bright.
Bright.
Unbelievably luminous. In astronomy, we distinguish between apparent brightness, how bright something looks from Earth, and intrinsic luminosity.
Which is how much actual energy the object is pumping out at the source.
Exactly. Given how far away these dots are, for us to even be able to see them as bright points of light, their intrinsic luminosity must be staggering.
How staggering?
They are pumping out energy on the scale of an entire galaxy.
Wait, I'm losing you. You just said they are unresolved. They are tiny pinpricks.
I did.
How can a tiny pinprick have the energy output of an entire galaxy?
That is exactly the headache. When you combine the compact size with the extreme luminosity, you run into severe physics problems.
I can imagine.
You have a massive, massive amount of energy pouring out of a very, very small, tight space.
Right. Usually to generate the luminosity of a galaxy, you need, well, a galaxy.
You need billions of stars spread out over thousands of light years. But here, all that power is crammed into a minuscule footprint.
So something very small, but it's burning with the intensity of billions of stars.
Yeah.
But the real kicker is the actual signature of the light, right?
Yeah.
The spectrum. Because we don't just look at the brightness, we break the light apart.
Right. When astronomers look at an object in space, they don't just take a pretty picture. They use a spectrograph to break the light down into its component wavelengths.
Creating a spectrum.
It's like taking a barcode of the light. This barcode tells them exactly what chemicals are present in the object.
Because different chemical elements absorb and emit light at very specific identifiable wavelengths.
Exactly. And the barcodes of these little red dots are completely bizarre.
Bizarre how? What are we seeing in the barcode that doesn't belong?
Two massive anomalies. First, they show patterns of hydrogen emission that simply do not make sense.
Hydrogen is the most abundant element in the universe, though.
It is. We know exactly how it behaves in young galaxies. We know how it behaves around black holes. We know how it behaves in star-forming regions.
But what's wrong with this hydrogen?
The hydrogen signature here, specifically what we call the Balmer lines, is incredibly broad.
Broad lines, what does that mean physically?
Broad emission lines usually mean the gas is moving at terrifyingly fast speeds, swirling around violently. But the specific shape of these lines in the LRDs is doing things our current models struggle to replicate.
Okay, so violently swirling hydrogen. And what is the second anomaly?
A massive, overwhelming abundance of nitrogen.
Nitrogen. Why is that weird? Nitrogen is everywhere. It's mostly what we are breathing right now in this room.
It's everywhere now. On a planet that has been around for 4.5 billion years, in a universe that is almost 14 billion years old.
Oh, right. We are looking back in time.
Remember, when we are looking at the universe when it was less than 1 billion years old.
Right.
In astrophysics, anything heavier than hydrogen and helium is considered a metal.
Wait, astronomers call nitrogen a metal?
Yeah, it's a quirk of the field. Everything heavier than helium is a metal. And in the early universe, metals barely existed.
Because they hadn't been made yet.
Right. Nitrogen is a byproduct of complex stellar nucleosynthesis. It takes generations of stars living, burning, and dying to slowly build up nitrogen in the cosmos.
So finding it early is bad.
Finding a massive concentration of nitrogen this early in the universe is like, well, it's like finding a fully refined plastic bottle in a prehistoric cave.
Ah, I see.
Chemical processes required to create it just shouldn't have had time to happen yet on this massive scale.
So let me get this straight. We have an object that is incredibly tiny. It is extremely red, suggesting dense dust.
Correct.
It is impossibly bright, outputting the energy of a galaxy from a pinprick.
Yes.
And its chemical barcode shows violently swirling hydrogen and a completely impossible amount of nitrogen.
You've got the whole rap sheet.
Why is that specific combination of clues so contradictory?
Well, as researchers like Devesh Nandal at the Harvard College Observatory pointed out in a recent analysis, these clues simply do not fit together under the normal rules of astrophysics.
You're dealing with mutually exclusive properties.
Exactly. How so? Well, if you have an object that is incredibly bright, it is usually huge and exposed, like a massive active galaxy.
Right, a big light shines brightly.
And the radiation pressure from all that intense light usually blows away any surrounding dust or gas.
It pushes it away.
Yes. Conversely, if you have an object that is very compact and red, it is usually something relatively dim and deeply obscured by a thick cloud of dust.
So it's either big and bright or small, dusty and dim.
Exactly. But here, the data is screaming that there is something unfathomably luminous, something generating an impossible amount of energy, hiding inside a remarkably dense, compact cloud of gas.
Okay, wait, let me try an analogy here. I want to make sure I really understand the contradiction.
Go for it.
Is it like trying to hide an atomic bomb detonation inside a cardboard box?
Oh, that's good.
Because the moment the energy goes off, it should completely obliterate the thing that is supposedly hiding it.
Exactly.
If the light source is that powerful, it should physically blow away the red dust cloud. But somehow, the dust cloud is still there, tightly wrapping this immense power source.
That is a much better analogy. Yes. The sheer radiation pressure, the physical force of the light itself should be violently expelling the gas and dust.
But it isn't.
No, the gas is holding on, remaining compact. Furthermore, the chemistry of that gas, that violently swirling hydrogen and the high nitrogen, is totally at odds with the sheer power of the light source hidden inside it.
It just shouldn't exist.
Standard astrophysics says you can't have all these things in the same place at the same time in the early universe.
But hold on a second. Astronomers have been studying the sky for a long time. They have a whole lineup of usual suspects when they find something powerful, compact, and bright, right? We can't be totally in the dark here.
We aren't. And when the James Webb Telescope first started sending back data on these little red dots, the astronomical community didn't just throw their hands up and quit.
We tried to solve it.
They immediately went to their lineup of usual suspects. They tried to pin this crime on the known actors in the universe. They tried to force the data into existing boxes.
So let's bring them into the interrogation room. We have our impossible crime scene. Who are the suspects and why didn't the charges stick? Let's start with the most obvious one.
Okay.
If we are looking at the early universe, shouldn't we just be looking at young galaxies?
That was suspect number one. We are looking at the first billion years, so maybe these are just incredibly dense, highly active young galaxies that are forming stars at a rapid rate.
Why doesn't that work? I mean, a galaxy has a lot of energy.
It falls apart entirely because of the spectrum, the barcode.
The chemistry.
Right. The bizarre, violently swirling patterns of hydrogen we talked about, and especially the abundance of nitrogen, just do not match the chemical fingerprint of a young galaxy.
Because they don't have metals yet.
Exactly. Young galaxies in the early universe are metal poor. They are mostly just vast, turbulent clouds of hydrogen and helium gas collapsing into the first generations of stars.
So they can't produce nitrogen.
They do not have the chemical maturity to produce the nitrogen signature we are seeing. Furthermore, young galaxies are messy.
Like the smudge you mentioned earlier.
Yes. They are sprawling. Even if they are dense, they don't look like unresolved, perfect pinpricks of light. They have a morphology, a shape that we can measure.
So the LRDs are just too small.
The LRDs are too small, too chemically complex, and too bright to just be normal young galaxies.
Okay, so if young galaxies don't have the right chemistry or shape, what does produce that much energy in a compact space? What about an AGN, an active galactic nucleus?
That was suspect number two.
Remind me what an AGN is.
An ordinary AGN is essentially a galaxy with a very active center, powered by a black hole that is moderately feeding on surrounding material.
Okay, so a feeding black hole.
But again, the models for ordinary AGNs could not explain the specific, weird hydrogen patterns, nor could they fully account for the nitrogen abundance in such a compact region.
So the barcode was fundamentally wrong again.
Exactly. The researchers also considered quasi-stars and massive starbursts, which are essentially concentrated regions of intense, rapid, and violent star formation.
But none of those fit either.
None of these usual suspects could satisfy all the clues simultaneously. They might explain the brightness, but not the compact shape.
Or they explain the shape, but not the chemistry.
Precisely. It's like trying to fit a square peg in a round hole.
Which naturally leads us to the biggest, baddest suspect in the universe. The one everyone assumes is responsible when there is an impossible amount of energy localized in a tiny space.
A growing, supermassive black hole.
A supermassive black hole.
Exactly. For a large portion of the astronomical community, a supermassive black hole seemed like the only logical answer left on the table.
Because what else could it be?
Right. In fact, many early papers on LRDs immediately concluded they must be heavily obscured black holes.
Let's talk about how a black hole actually makes light. Because, black holes themselves are, well, black.
Right. Their gravity is so strong not even light can escape.
So how does a black hole explain an incredibly bright red dot?
It's all about the feeding process. When a supermassive black hole is actively growing, it exerts a massive gravitational pull on all the gas, dust, and stars around it.
It pulls everything in.
But as that material gets pulled in, it doesn't just fall straight down, it spirals inward, like water going down a drain.
Swirling around.
Yes. This creates what we call an accretion disk.
And because it's spiraling so fast, there's a lot of friction.
An unfathomable amount of friction. The gas is moving at a significant fraction of the speed of light.
Wow.
The gas particles are smashing into each other, compressing and heating up due to sheer friction and gravitational compression.
So it gets hot.
This accretion disk gets incredibly hot, millions of degrees hot, and as a result, it shines with unbelievable brilliance.
So the disk itself is the light source.
Yes, the disk itself becomes one of the brightest objects in the universe, entirely outshining the host galaxy. This phenomenon is a quasar.
And a quasar can provide the intrinsic luminosity required to make these objects so bright from billions of light years away.
It absolutely can.
And it fits the compact clue perfectly, right?
Yeah.
Because a black hole and its accretion disk are tiny compared to a whole galaxy.
Exactly. It fits the compact size, it provides the required energy output, and you can even build theoretical models where the surrounding gas and dust obscure the black hole, making it look red.
So it seems like a solid open and shut case.
It really did. But here is the massive twist in the story, and what makes this such a thrilling scientific detective story.
Wait. I feel like I know where this is going. If it's the black hole eating that much material, shouldn't we see other evidence of it?
What's fascinating here is precisely what we are not seeing.
The missing evidence.
Yes. When a supermassive black hole is actively growing and eating matter at the rate required to power these little red dots, it is not a quiet or contained process.
They're messy.
It is violently messy. That superheated accretion disk doesn't just emit visible or infrared light. It screams across the electromagnetic spectrum.
Right.
Because the gas is heated to millions of degrees, standard thermodynamics, specifically black body radiation, dictates that the peak emission of that energy must be in the form of high-energy radiation.
So like X-rays.
Exactly. It blasts out intense X-ray radiation and powerful radio waves.
Let me guess. James Webb doesn't see X-rays.
James Webb is an infrared telescope, correct? It doesn't see X-rays.
So how do we know they are missing?
Because we have other telescopes, like the Chandra X-ray Observatory, which has been staring at these exact same patches of sky.
Oh, I see.
If these little red dots were powered by rapidly growing supermassive black holes, our X-ray telescopes should be absolutely blinded by the high-energy emissions coming from them.
But I'm going back to my bomb in a cardboard box analogy.
Yeah.
Could the thick red dust cloud the cocoon just be blocking the X-rays?
That's a great thought.
If it's dense enough to make the light red, maybe it's dense enough to hide the X-rays too?
It's a very logical thought, and astronomers absolutely considered it. It's a known phenomenon called a Compton-thick AGN.
Compton-thick, okay.
If the gas is incredibly dense, it can absorb what we call soft X-rays.
But there are hard X-rays too.
Yes, but it cannot absorb hard X-rays. Hard X-rays are so energetic, they punch right through almost any amount of gas and dust.
Like an X-ray at the doctor's office going right through your skin.
Exactly. If there is an accretion disk burning hot enough to power an LRD, the hard X-rays must escape. And yet, when we look at the locations of these little red dots with our best X-ray observatories, there is nothing.
Nothing at all.
A deafening silence in those frequencies. Many of the observed little red dots lack the strong X-ray or radio emission that is the absolute non-negotiable hallmark of a growing supermassive black hole.
This is wild. It's like arriving at the scene of what you think is a massive chemical explosion. A building is completely leveled. The energy required to do it is off the charts.
Right.
You assume it was a bomb. But when you investigate, there is absolutely zero heat signature. There are no scorch marks, no chemical residue from explosives, no fire damage whatsoever.
That is exactly what this is like.
The sheer absence of the scorch marks the absence of the X-rays is just as important, if not more important, than the presence of the bright red light.
It completely rules out the most logical explanation. The prime suspect has an airtight alibi.
It must be incredibly frustrating for scientists when current models completely fail like this.
It is. You have a pristine data set from the most advanced telescope in human history, and none of your established theories can explain it.
The young galaxies don't have the chemistry.
Right.
The normal AGNs don't fit the profile. And the supermassive black holes are missing their critical X-ray signature.
It forces a paradigm shift in the field. It forces the astrophysics community to stop trying to cram the data into old boxes and instead imagine something entirely new.
So if it's not a black hole, and it's not a normal young galaxy, and it's not an AGN, we're completely out of options on the standard list.
We are.
What could possibly be that bright, that compact, have that specific weird chemistry with all the nitrogen, but be completely quiet in X-rays? We need a completely new suspect.
And that is exactly what researchers like Devesh Nindal and his collaborators have provided. They have introduced a completely new central engine to explain the mystery.
A new engine. Okay, what is it?
They looked at the physics, they ran the complex simulations, and they proposed that hiding inside that dense red cocoon of gas is a single star.
A star. Just one star.
But not just any star, a supermassive star. An absolute monster with a mass around 100,000 times that of our sun.
Okay, hold on. A single star. 100,000 times the mass of our sun.
Yes.
I need you to help put that into perspective, because those numbers are so big, they just sound like abstract math to me.
It's hard to visualize, I know.
Our sun is already mind-bogglingly huge. You can fit over 1 million Earths inside our sun. And you are telling me this theory proposes a single star that is 100,000 times heavier than that.
It stretches the limits of imagination, honestly. The scale is almost incomprehensible.
How big do normal massive stars get?
When we talk about massive stars in our modern universe today, a really big star, like an O-type main sequence star, might be 50, maybe 100 times the mass of our sun.
Okay.
The absolute theoretical maximum we usually see, like the star R136A1 in the Tarantula Nebula, is around 250 to 300 solar masses.
And that's the absolute max.
And those stars are so unstable, they're actively blowing themselves apart with their own radiation.
Right.
To suggest a star of 100,000 solar masses is to suggest a monstrous anomaly that defies everything we know about how stars live today.
Wait, I thought there was a physical limit to how big a star could get. Doesn't the light itself push the star apart?
You are talking about the Eddington limit, and you are absolutely right.
The Eddington limit.
Yes. The Eddington limit is the point where the outward pressure of a star's radiation exceeds the inward pull of its own gravity.
Okay, so the star is shining so brightly, the physical force of the light pushes the gas away.
Exactly. In the modern universe, if a star gets too massive, the sheer intensity of its nuclear fusion creates so much outward radiation pressure that it literally blows the outer layers of the star away into space.
It basically starves itself of mass.
Right. It prevents the star from growing any larger. So under modern conditions, a 100,000 solar mass star is physically impossible. It would destroy itself before it ever formed.
So how does Nandal's theory get around the Eddington limit? How does this monster even exist?
Because the early universe was a fundamentally different environment. Remember, we are talking about the first billion years.
When it was mostly hydrogen and helium.
Exactly. The universe was pristine. There were no metals, no carbon, no oxygen, no iron.
Why do metals matter for star formation?
In modern star formation, these metals act as cooling agents.
Cooling agents.
Yeah, they allow giant gas clouds to cool down and fragment into hundreds or thousands of smaller clumps, which then become normal-sized stars.
Oh, I see. The metals help break the cloud up.
Precisely. But in the early metal-free universe, a massive cloud of pristine hydrogen gas couldn't cool efficiently. It couldn't fragment easily.
So it stays together.
Yes. So instead of breaking apart into a cluster of normal stars, the entire massive cloud could undergo a monolithic catastrophic collapse under its own gravity.
Just one giant collapse.
Drawing in vast amounts of material so quickly that it overwhelms the Eddington limit, forming a single supermassive stellar core.
Here's where it gets really interesting. So you have this pristine environment allowing for a massive freak of nature star to form.
Yes.
And this single model, this one colossal object, can explain all the clues.
Everything. According to this research, a supermassive star of this exact scale, around 100,000 solar masses, is the exact key that unlocks the entire mystery.
Let's run down the checklist.
The researchers showed that a supermassive star can provide the intense intrinsic luminosity required to match the little red dots.
Okay, it's bright enough. What about the missing X-rays?
Because it's a star undergoing fusion, not an accretion disk superheated by friction, it doesn't produce the hard X-rays that a black hole does.
Wow. It perfectly explains the missing X-ray evidence.
Exactly. It is such an elegant and effective solution that it is changing the entire conversation in astronomy right now.
I can imagine.
Even competing scientific scenarios. Researchers who were desperately trying to make the black hole models work by inventing incredibly complex dust-blocking geometries are now starting to pivot and invoke these supermassive stars as the central engine.
It's taking the field by storm.
It really is.
It is just amazing to marvel at the conditions of the early universe. The fact that the cosmos had the exact right environment, the right density of raw materials to allow for these singular titanic entities.
It was a very different time.
But wait, I'm still trying to picture this thing. If our sun is a single heavy bowling ball,
Okay.
this supermassive star is not just a pile of bowling balls. It's like an incredibly volatile, overpressurized industrial boiler the size of a mountain, fighting a constant, terrifying battle against its own internal energy.
That is a much better analogy, because a supermassive star isn't just sitting there peacefully fusing hydrogen like our sun.
It's fighting itself.
That battle you just mentioned, the tug-of-war between gravity pulling 100,000 solar masses inward and the immense, almost unimaginable nuclear fusion pushing outward, is the crucial next piece of the puzzle.
Because just being massive doesn't solve the whole crime scene.
No, it doesn't.
Right, because the clue wasn't just that it was bright. The clue was that it was a compact red dot.
The cocoon.
Yes, it was hiding in a dense cocoon of gas.
Yeah.
If you have an overpressurized industrial boiler the size of a mountain burning that brightly, how do you not just see a blinding white light?
That's the question.
Where does the red dust cloud actually come from? How does the star build its own hiding place? If the light is that intense, shouldn't it clear the area around it?
To answer that, we have to look deeply into the fluid dynamics and the unique, highly violent life cycle of these monster stars.
Fluid dynamics.
Yeah, and specifically how they manage mass loss. Stars are not static objects. They are fluid dynamic systems in a constant, delicate equilibrium. And when you have 100,000 solar masses of gravity fighting 100,000 solar masses of fusion, that equilibrium is inherently unstable.
What happens when it loses that balance?
Well, now, in a typical, relatively normal star, mass loss happens relatively smoothly late in life.
Smoothly.
Think of our sun. Billions of years from now, as its core changes, it will slowly swell up into a red giant.
Right, expanding slowly.
Its outer layers will become loosely bound by gravity, and they will gently puff away into space, creating a beautiful, somewhat serene planetary nebula.
A gentle shedding process.
Yes, it is a continuous, gradual shedding process driven by a steady stellar wind. But supermassive monsters do not behave like that.
They aren't gentle.
The physics simply won't allow a steady wind. The researchers analyzed the internal structures of these theoretical giants, and they found that they experience something completely different.
What do they experience?
They undergo what researchers call strange mode pulsations.
Strange mode. That sounds ominous.
It is a bit ominous, yes.
What exactly is the physics behind a strange mode pulsation? Why is it strange?
It has to do with how light moves through the interior of the star. Deep inside the star, there are layers of gas that can become opaque.
Opaque, meaning light can't easily pass through them.
Exactly. This is often related to the ionization of helium, a process known as the Kappa mechanism.
Okay, let's break that down. The light gets trapped.
Exactly. The immense radiation pushing out from the core hits this opaque layer and gets trapped. It acts like a dam.
Oh, I see.
The radiation pressure builds and builds, superheating this specific layer. The pressure becomes so intense that it overcomes gravity entirely.
So what happens to the layer?
This specific layer of the star violently heaves outward, pushing massive amounts of stellar material into space.
An explosion.
Sort of, but as it expands outward, the gas cools down. And as it cools, the helium recombines.
And what does that do?
The gas suddenly becomes transparent again, and the trapped light instantly escapes.
Like opening the safety valve on the boiler.
Yes, and because the pressure is suddenly released, gravity takes over again, and the outer layers of the star crash back down inward.
Until they heat up again.
Until they heat up, become opaque, trap the light, and the pressure builds to the breaking point again.
This is strange mode behavior.
Yes. It is not a gentle shedding. It is characterized by discrete, incredibly powerful pulsation episodes.
So the star is basically having a fit.
The star is fundamentally unstable. It literally heaves outward, violently ejecting massive shell-like shapes of gas all at once. And then it settles back down until the pressure builds, and it violently heaves another massive shell out.
If we connect this to the bigger picture of stellar evolution, It is completely foreign to what we usually observe.
Completely foreign.
Most stars die in a somewhat predictable continuous shedding, or they go out in one sudden final supernova explosion.
Right, a one-and-done deal.
But this isn't a final explosion. This is a rhythmic, repeating, violent coughing fit that lasts for thousands of years.
Exactly. And the strange mode pulsation mechanism is the precise physical process that solves the morphology problem.
The morphology problem. You mean why the little red dots look so compact and dense to the telescope?
Yes. Every single time the supermassive star undergoes one of these strange mode pulsations, it blasts out a massive, distinct shell of gas.
A shell.
Over time, it creates multiple shells, layered one over the other, wrapping itself tightly in dense material.
Oh, I get it. It's taking a deep, massive breath and violently exhaling an expanding shell of dense gas.
Perfect.
And then it takes another breath and exhales another shell right inside the first one. Over and over again.
Yeah.
It is creating a nested Russian doll of dense gas shells entirely around itself.
Yes, and because these shells are being ejected so violently and repeatedly, they form a highly compact, dense region directly surrounding the star.
So the gas doesn't just float away.
The material doesn't have time to dissipate into the wider galaxy before the next shell slams into it.
So they stack up.
So when the telescope looks at it, it doesn't see a wide, sprawling cloud of typical stellar formation. It sees a tight, incredibly dense knot of ejected gas illuminated from within by the star's immense luminosity.
The star is literally wrapping itself in thick layers of its own expelled guts.
It is building its own cocoon, yes.
So the extreme redness is because all that intense light has to push through this incredibly thick, nested Russian doll of gas.
Exactly.
It's like a cosmic heartbeat that violently ejects mass with every single beat, building its own cocoon.
A cosmic heartbeat is a fantastic way to describe it. But this heartbeat does more than just build a wall of dust around the star.
What else does it do?
It doesn't just create the shell, it fundamentally alters the nature of the light that escapes. It completely changes the chemical signature, the barcode of the light we eventually see in our telescopes.
Which brings us back to the most perplexing clue of all, the spectrum.
The barcode.
Right. We have the compact shape explained by the heartbeat, the nested shells of gas.
Oh.
We have the missing X-rays explained, because it's a star, not a black hole.
Check.
But we still have to explain the violently moving hydrogen and that totally impossible, crazy amount of nitrogen.
The trickiest part.
If the early universe didn't have nitrogen, where did it come from?
And this is where the elegance of Nandal's model truly shines, because it delves into the nuclear astrophysics of the star itself.
Okay, let's dive into the core.
We have to look at what those ejected shells are actually made of. The composition of the cocoon.
Okay.
The raw material collapsing to form the star was just pristine hydrogen and helium, right?
Right, the early universe stuff.
But inside a 100,000 solar mass star, the core temperature and pressure are so unimaginably extreme that standard hydrogen fusion isn't enough to hold the star up.
It needs a stronger engine.
The star relies on a different process called the CNO cycle.
CNO, carbon, nitrogen, oxygen. But you just said this didn't exist yet.
They existed in barely traceable microscopic amounts, perhaps, seeded by the very, very first short-lived generation of normal, massive stars that lived and died right before this.
So just tiny trace amounts?
Right. But in a supermassive star, those trace amounts are all it needs to kickstart the engine.
How does the CNO cycle work?
The CNO cycle uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium much faster and hotter than normal fusion.
Okay.
But the cycle has a bottleneck. One of the steps turning nitrogen into oxygen is very slow.
Let me guess. Because it's slow, the process gets backed up.
Exactly. It's like a traffic jam on a highway. The carbon and oxygen quickly turn into nitrogen, but the nitrogen can't move to the next step fast enough.
So it just accumulates.
Deep in the core of this supermassive star, a massive stockpile of nitrogen begins to build up. It becomes highly enriched in nitrogen.
Okay, but that nitrogen is deep in the core. The light we see from the little red dots is coming from the cocoon on the outside.
Right.
How does the nitrogen get out of the core?
Convection.
Like a boiling pot of water.
The heat inside the star is so intense that the plasma actually boils, exactly like water in a pot. Vast convection currents dredge that freshly minted nitrogen up from the core all the way to the outer layers of the star.
It brings the nitrogen to the surface.
And then the strange mode pulsations happen, the heartbeat.
Mm-hmm.
When the star violently heaves outward, blasting off its outer layers to form the cocoon, It is blasting out gas that has been heavily processed and enriched with nitrogen.
Oh, wow. So the cocoon isn't just basic primordial gas.
Not at all.
It is a highly specific, customized chemical mixture that the star itself cooked up in its core, brought to the surface, and then violently coughed out.
Precisely. And this leads to a profound realization, one that Devesh Nandal highlighted perfectly in his analysis.
What did she realize?
He explained that the spectrum, the barcode of light, and the morphology, the physical shape and compactness of the object are actually two sides of the very same physical problem.
I want to make sure I am grasping that fully. How are the shape and the light barcode the exact same physical thing?
Well, the spectrum tells us what is making the light and how it's being chemically processed.
Okay.
It tells us that there is an intensely bright light pushing through a fast-moving, turbulent layer of hydrogen, helium, and specifically nitrogen.
Right.
The morphology, the tight dot shape we see in the telescope, tells us how tightly packed and dense that surrounding material is.
And the model explains both.
The strange mode pulsation model explains both perfectly at the same time. The violent heartbeat creates the dense, tight shape by throwing off shells of gas.
Yes.
And because that same heartbeat is coughing out the nitrogen-rich processed gas dredged up from the core, it forces the star's brilliant light to filter through those exact chemicals, creating the specific barcode we observe.
Let me try to visualize this. It is like, imagine the supermassive star itself is a blindingly bright, pure white flashlight. But the gas shells, those nested Russian dolls, created by the strange mode heartbeat, act like incredibly complex, dense, stained glass windows made specifically out of hydrogen, helium, and nitrogen.
I love the stained glass analogy.
Right, because we are 13 billion light years away. We can't actually see the white flashlight at the center. It's too small, too far, and entirely covered.
Obscured entirely.
But we can see the intensely powerful light shining through the stained glass.
Yeah.
And by looking at the very specific colors and missing lines in the spectrum shining through, we know exactly what chemicals are in the glass.
We know the glass is moving incredibly fast.
Right, and we can calculate exactly how powerful the bulb inside must be to push light through such a dense, complex window.
That is a phenomenal way to put it. The stained glass is moving, it's turbulent, and it's heavily rich in nitrogen.
And this completely ties up all the loose ends that were driving the community crazy.
All of them. That nitrogen abundance, which was previously a massive thorn in the side of astronomers trying to use young galaxy models, is no longer a problem.
It's not a bug, it's a feature.
In fact, it is the opposite of a problem. The nitrogen anomaly is now the primary piece of smoking gun evidence proving the giant star theory.
It proves the star is cooking it.
Observations of little red dots are continuing to reveal these nitrogen-rich spectra, and every time they do, it serves as another confirmation that there is a supermassive, strange mode pulsating star inside, cooking up that nitrogen and blasting it into its own cocoon.
It is so incredibly satisfying when a single cohesive theory just clicks all the disparate pieces into place like that.
It's what physicists live for.
It honors the data instead of ignoring the inconvenient parts. But I have to ask about the long-term reality here.
The lifespan.
Yeah, an overpressurized boiler the size of a mountain, violently pulsating, blowing out nested shells of heavy gas, constantly losing mass.
Yeah.
That is an incredibly unstable, unsustainable situation.
Highly unsustainable.
So what does this all mean for the fate of this monster star? It can't just keep pulsating and dredging up nitrogen forever, right? It has to eventually run out of fuel or finally lose that epic tug-of-war against gravity.
It absolutely does. The lifespan of a supermassive star is incredibly short in cosmic terms.
How short?
Perhaps only a few 100,000 to a couple of million years, which is a blink of an eye compared to our sun's 10 billion year lifespan.
Oh, wow, that is short.
And the end of this star's life is just as extreme, if not more extreme, than its existence.
What happened?
Because when a star of this impossible magnitude finally reaches the end of its life, it doesn't do what normal stars do. It undergoes a process known as direct collapse.
Direct collapse, that sounds immediate. What exactly happens? Is it just blink out?
It is the ultimate final act of the struggle between gravity and pressure. After its very last strange mode ejection, after it has coughed out its final shell of gas and exhausted the nuclear fuel in its core, the outward radiation pressure simply ceases.
The engine turns off.
Now, a normal, massive star, say, 50 solar masses would undergo a core collapse supernova.
Right, a giant explosion.
The core would collapse into a neutron star or a small black hole, and the rebound energy would rip the outer layers of the star apart in a massive, spectacular explosion.
But not our 100,000 solar mass monster.
No. The physics of hypermassive objects are governed by general relativity as much as thermodynamics.
Okay, getting heavy now.
In a star this massive, as the core contracts and heats up to unimaginable temperatures to try and find a new fuel source, it encounters a phenomenon like pair instability or photodisintegration.
Photodisintegration, what is that?
The extreme high-energy gamma rays in the core suddenly start converting into electron-positron pairs, or they start literally shattering the atomic nuclei themselves.
Shattering atoms.
Both of these processes consume immense amounts of energy. The internal pressure drops precipitously. It's like pulling the floor out from under a skyscraper.
So gravity just wins.
Yeah.
Instantly.
Yeah. Gravity wins overwhelmingly. The mass of the star is so great and the gravitational pull so intense that it entirely bypasses the supernova explosion.
Bypasses it. It doesn't explode.
The gravitational binding energy is simply too strong for any explosion to overcome. The star immediately folds in on itself.
That is terrifying.
All that mass, tens of thousands of solar masses, crushes downward. An event horizon forms inside the collapsing star, swallowing it from the inside out.
Swallows itself.
It instantly forms the colossal seed of a supermassive black hole.
This raises an important question. If it collapses directly into a black hole of that size, does that mean these monster stars are actually the missing link to understanding black holes in the early universe?
Yes.
Because I know that has been another huge mystery.
This is perhaps the most profound and far-reaching implication of the entire study.
The black hole problem.
Right. For a long time, astronomers have been completely puzzled by how supermassive black holes got so big, so fast in the early universe.
Because we see them, right?
Yes. When we look at quasars just a few 100 million years after the Big Bang, we see black holes that are 1 billion times the mass of our sun.
And if black holes have to start small, from the death of a normal star, and grow by slowly eating matter?
Exactly. They run into the Eddington limit again. A black hole can only eat matter so fast before the radiation from its accretion disk blows the surrounding food away.
It's a speed limit for eating.
If they start at 10 or 50 solar masses, there simply wasn't enough time in the first billion years of the universe for them to reach 1 billion solar masses.
Math just doesn't add up.
The timeline flat out didn't work. It's like finding a fully grown adult human in a kindergarten class. It defies the growth rate.
But this model, this provides a shortcut.
It provides a brilliant, elegant origin story. It skips the traditional, agonizingly slow growth phase.
Because it starts massive.
It offers a mechanism where a massive 100,000 solar mass seed is planted directly into the universe by the immediate collapse of one of these monster stars.
It skips the line.
It gives the supermassive black holes an enormous head start, solving the timeline crisis perfectly.
Just consider the sheer violence and the absolute finality of a direct collapse.
It is staggering.
There is no grand supernova lighting up the galaxy. There is no lingering, glowing remnant slowly fading away over millennia.
None.
It is just a colossal, titanic object, a star that dwarfs anything we can easily comprehend, violently dominating its local space, churning out nitrogen in strange mode pulsations.
Emitting all that light.
And then, in a fraction of a second, the pressure drops. It simply folds out of existence. It swallows itself whole and vanishes into a singularity, leaving only its gravitational ghost and its nitrogen-rich cocoon behind.
It is breathtaking astrophysics. It brings together so many independent, baffling astronomical clues into one beautifully unified physical picture.
It ties everything up.
We started with the mystery of the little red dots and their bizarre chemistry, and we ended up solving the origin story of the earliest supermassive black holes.
The LRDs are the missing link.
The little red dots are essentially the active, pulsating cocoons of these black hole seeds right before they undergo direct collapse.
It is like the ultimate cosmic magic trick. You have a star 100,000 times heavier than the sun. It pulses violently over and over, drawing everyone's attention by wrapping itself in this glowing, complex, nitrogen-rich cloak of red gas.
The ultimate misdirection.
It builds all this tension, radiating all this power. And then, without the standard explosive flash, without the fireworks of a supernova to announce its exit, it simply vanishes into a black hole.
It pulls the trapdoor on itself?
But I have to push back here, or at least ask the obvious skeptical question. We are talking about a lot of highly complex theory here.
Of course. Skepticism is good.
If the climax of this entire theory is that the star simply disappears into a black hole, skipping the explosion, how can we ever prove it?
That is the challenge.
You can't observe an invisible collapse inside an opaque cloud of gas. How do you prove the existence of something that hides in a cocoon and then turns completely invisible? Is this just unprovable math?
That is the most critical question, and it represents the exact next step for the scientific community.
Okay, how do they solve it?
It is a fascinating example of how the scientific method works in real time at the very edge of human knowledge. You are right, the proof won't be in seeing the direct collapse itself because it is inherently dark and incredibly fast.
Right.
We will likely never catch one in the exact millisecond it happens. The proof will be in proving the exact predictive chemistry of the cloak it leaves behind the little red dot itself.
So how do they do that? How do you test it?
By predicting the unseen.
Predicting the unseen.
You build a mathematical model that explains past observations, which Nandal and his team have done brilliantly. But to truly prove a theory in physics, your model must be able to boldly predict future observations.
It has to make a testable claim.
You have to put your neck on the line and say, if my underlying physics regarding strange mode pulsations and CNO cycle nitrogen enhancement are correct, then the next time we look at one of these objects with this specific instrument, we will see exactly this highly specific pattern.
So they're laying down a wager on future James Webb data.
Precisely. The researchers are now turning the internal thermodynamics and fluid dynamics of these supermassive stars into full, incredibly detailed predictions for the specific spectra of little red dots.
Making a template.
They are using advanced radiative transfer codes to calculate exactly what the barcode should look like down to the finest detail.
Down to the exact line.
They are predicting the exact ratios of nitrogen to carbon, the exact widths of the hydrogen Balmer lines, and the exact infrared flux we should expect.
It's like they have studied the historical clues, they've figured out the pirate's logic for hiding the treasure, and now they have drawn a highly specific treasure map based on that logic.
I love that.
They have marked a very precise X on the map, and now they're just waiting for the James Webb Telescope to dig at that exact spot to measure the exact light spectrum of newly discovered little red dots to see if the treasure, the exact barcode they predicted, is actually buried there.
And that is exactly what is happening right now in observational astronomy. They are preparing those exact spectral predictions so that future James Webb observation cycles can directly test and confirm their supermassive star theory.
And if it matches?
If the telescope points at a new little red dot and the light spectrum comes back matching Nandal's incredibly specific theoretical predictions, it will be the ultimate confirmation.
It becomes real.
It moves from an elegant hypothesis to a confirmed physical reality.
It is so incredibly exciting to be sitting on the cutting edge of this right now. We are talking about a groundbreaking theory right as the greatest telescope in human history is warming up its instruments to test it.
The timing is perfect.
If the James Webb Telescope confirms these detailed spectra, it fundamentally rewrites our understanding of the early universe.
It rewrites the textbooks.
It confirms that the cosmos wasn't just filled with slow-growing young galaxies and slowly feeding black holes. It was once populated by these pulsating, monstrously unstable stars acting as rapid-fire black hole factories.
It completely changes the narrative of cosmic history. It takes these anomalous, annoying little red dots that were breaking our models and turns them into the foundational engines of the universe we see today.
It explains the chemistry, the light, and the black holes all in one stroke.
It does.
What an unbelievable journey this has been today. We started with a handful of completely unexplained, highly luminous little red dots that were baffling astronomers because they lacked the expected X-rays of an accreting black hole.
The impossible puzzle.
We followed the clues, the compact shape, the intense luminosity, the bizarre nitrogen-rich spectra, to the revelation of an absolute monster, a 100,000 solar mass star.
A true cosmic giant.
We learned how these giants fight a terrifying battle against their own gravity, pulsing in a strange mode to violently cough out massive shells of core process gas, building a dense, nitrogen-rich chemical cocoon around themselves.
The Russian doll of gas.
And finally, we saw how their existence ends in a terrifying direct collapse, instantly bypassing a supernova to seed the young universe with the supermassive black holes that anchor galaxies today.
It is a profound testament to the power of observation. When the data doesn't fit the theory, you don't throw out the data.
You change the theory.
You embrace the anomaly and you apply rigorous, imaginative theoretical physics until a new, clearer picture of the universe emerges.
I want to leave you with a final thought to mull over as you look up at the night sky tonight.
Okay, let's hear it.
We used to think the universe grew up slowly, methodically, building itself piece by piece. But if this theory holds true, if the earliest, most massive black holes in our entire universe didn't just grow slowly from dust, but were instead instantly born from the direct collapse of these monstrous, violently pulsating stars hiding inside their own red gas shells.
It makes you wonder about everything else we see.
It really does. What other tiny, seemingly insignificant dots in our night sky are buried deep in our telescope data are actually the colossal dying engines that built the modern universe?
A great question.
If the supermassive black holes that sit at the center of almost every galaxy today, including our own Milky Way, came from the instant death of these monsters, are we essentially entirely surrounded by the gravitational ghosts of supermassive stars? Keep looking up and keep questioning what you see.